All right, let's dive right in. Today, we're tackling a really fascinating challenge. How do you take a massive computer simulation, which is really just a giant pile of numbers, and turn it into a dynamic, visual story that actually makes sense?
I mean, think about it for a second. Air is, well, it's invisible, right? So how in the world can engineers and designers possibly understand the incredibly complex dance it does when a car is slicing through it? That's the exact question we're going to answer.
So, here's our game plan. We're going to build this whole visualization layer by layer. First, we'll turn that raw data into an actual car. Then we'll zoom in on the most important area, trace the air's path, actually give color to things like turbulence, and finally, we'll bring the whole shebang to life with animation. Let's get started.
Okay, first things first. We have to start somewhere, right? And that's taking all this abstract simulation data and giving it a physical form, something we can actually look at and interact with.
So, on the left you see what we start with. Literally just file names. It's just numbers. But then, on the right, boom. That's our first big step. By rendering the car's geometry coordinates as a point cloud, it's kind of like a 3D connect the dots puzzle, and all of a sudden, a car just pops into view.
And you know, it sounds complicated, but getting here is actually pretty straightforward. We just import the data, tell the software to render it as points, and then, spin the model around so it's facing the right way. That's it. In just a few clicks, we've gone from a spreadsheet of numbers to something that actually looks like a car.
Okay, so we've got our car. Awesome. But now what? I mean, a simulation like this can cover a huge area, but the really interesting stuff, all the chaotic physics, is happening right behind the vehicle. So that's where we need to focus our attention.
The way we do that is with something called a region of interest, or just ROI. And honestly, the best way to think about it is like a digital magnifying glass, or maybe a big, invisible box. We're basically telling the computer, hey, see this box? This is what matters. You can kind of ignore everything else for now. All the action is happening right in here.
So we take that digital box and we place it perfectly around the back of the car. This area, which is called the wake, is where all the air gets churned up after it flows past the vehicle. By isolating it like this, we can analyze all that complexity in much greater detail, without making our computer sweat over stuff we don't care about.
All right, we've got the car, we've got our focus area locked in. Now for the really cool part. It's time to actually see the air move by drawing these invisible highways that it travels on.
We do this by creating what are called streamlines. And that digital smoke trail analogy, it's absolutely perfect. Seriously, just picture that. Each and every one of these lines shows you the exact, precise path that one little particle of air would take as it zips over and around the car.
So how do we make them? Well, conceptually, it's pretty simple. First, you drop a starting point. They call it a seed, right in front of the car. Then, you point the software to all the velocity data from the simulation, and finally, it just draws the paths that start from that seed. But, and this is key, it only shows us the parts that are inside that region of interest we already set up. Pretty smart, right?
And look at that. Just like that, the invisible is suddenly visible. What we have now is this beautiful, intricate map that shows us exactly what the air is doing. You can see right where it's flowing all smooth and clean over the hood, and you can pinpoint the exact spot where it starts to get messy and tumble off the back.
But seeing the path of the air is just one piece of the puzzle. What about the air itself? What's its character? Is it calm, or is it wild and chaotic? Our next layer is going to show us exactly that.
So to do this, we switch gears. We stop looking at the velocity data for a second, and we focus on a different variable in the simulation. It's called eddy viscosity. Yeah, I know, it's a technical term, but all you need to know is that it's basically a turbulence meter. High value, the air is chaotic. Low value, the air is smooth sailing.
And we visualize this using a technique called volume rendering. So instead of just lines, we're rendering a whole 3D field. This transforms the abstract idea of turbulence into something we can actually see, this dense, cloud-like structure that shows us exactly where the most chaotic air is churning away behind the car. Okay, let's take a step back. We've built up this amazing picture, right? We've got the car's shape, the path of the air, and even the location of the turbulence. But everything we've seen so far, it's all been a snapshot, a single frozen moment in time. So, for our final and honestly most exciting step, let's hit play. Yeah, every single thing we've created, every point, every line, that turbulence cloud, it's all just one frame from a much bigger movie.
It's incredibly insightful, don't get me wrong, but it doesn't quite capture the life, the dynamic nature of airflow.
But what if we could? What if we could actually press play and just watch the air move, almost in real time? I mean, that's the ultimate goal, isn't it? To not just look at a map of the flow, but to watch the flow, well, flow. To see all those little eddies and vortices being born and then just disappearing, as if we were really there.
Well, we can do exactly that. By setting up an emitter in front of the car that continuously releases virtual particles, and then telling those particles to follow the velocity data over time, we bring the entire simulation to life. We are no longer looking at a static picture. We are watching the physics unfold right in front of our eyes.
So let's do a quick recap of the tools in our toolbox here. We used points just to get the basic shape and structure. We used streamlines to trace the exact path the air is taking. We used volume rendering to see the density of something, in our case, turbulence. And there are other tools too, like a slice plane, which can give you a nice 2D cutaway view wherever you want.
But here's the most important thing to remember. No single one of these techniques tells the whole story. Not even close. The real magic happens when you start layering them on top of each other. Each one is like a different lens you can look through. And when you combine them, that's when you get the complete, detailed picture of what's really going on.
So think about where we started. We had nothing but numbers on a computer, and we ended up with this living, breathing animation of airflow. It just goes to show you, with the right tools and the right approach, we can make pretty much any invisible force visible. Which kind of leaves you wondering, doesn't it? What other hidden worlds, from the heat flowing through a tiny microchip to the pressures inside a beating heart, are just sitting there in the data, waiting for us to bring them to life?